All right, any questions?
That's just it.
On whatever.
I was having a hard time with Mars and the base dropping.
All right, I'm gonna make up numbers here.
Do you want the gravity or what?
I'm gonna make up something. So let's assume we're on some planet with G of 5 meters per second squared. I know Mars is less. We dropped it from a window and let's say 10 meters, and then it's going to break in 0.0, I think I had it in millimeters, but 0.006 meters, 6 millimeters. I think it was less on the problem part, 5, okay. If we're ignoring air resistance, then this thing will fall at a constant rate until it hits the ground. Once it hits the ground, it is going to, we have now introduced a new force, acceleration will change. So the idea was to break it up into two pieces. One, there's a falling piece, and the second is the stopping piece. While it is falling, it was dropped. So what's the initial velocity? Okay. Initial velocity, 0. Yes. By the definition of what dropping means. Otherwise it's thrown, projected, something like that. I know that the displacement for something that is dropped is going to be 1/2 gt squared. So I think the first question was, what was the time it takes to fall? But you're basically plugging into this. So it'd be 10 is equal to 1/2 5 t squared. And in this particular case, you get t is equal to 2 seconds. The next question was, how fast is it going just before it hits? Or I might even say, how fast is it going when it hits? That's in physics, that's the language that we use, that how fast it's going when it hits or just before it hits mean the same thing. So we just need to figure out, well, I know that it increases by 5 meters per second every second. It's falling for 2 seconds. So how fast is it going when it hits? Let's look at it differently. When time is 0, the speed is 0. It's going to fall for 2 seconds. The acceleration is 5 meters per second squared, which means 5 meters per second. The velocity will change 5 meters per second every second. So how, after 1 second, it's going
4, 5,
after 2.
10.
If you're using the equation from the book, Hewitt gives an equation that for something that is dropped, that you need a speed. I guess officially that. But you just take the acceleration times time. If the initial speed is not 0, then you can't do this formula. This assumes that initially an object is dropped starting from rest. Otherwise, what this tells us actually is the change in velocity. So it's going 10 meters per second right before it hits. So the average velocity, well, it starts at 0 meters per second, and at this point it's going 10 meters per second. And too many of these numbers keep showing up again, so, but we're here. What's the average velocity? Yeah. What's the average? So now it's going to stop. It's going 10 meters per second just before it stops. It's gonna stop in 0.006 meters. I think in the problem I said, assume that the acceleration is constant while it's stopping. Well, when it stops, how fast is it going? I saw the hand gesture. So if it's going 10 meters per second at the beginning of that phase and 0 meters per second at the end of the phase, what's the average velocity? Yeah, it's just the midpoint. So my average velocity here is also 5 meters per second. Okay, then what is the time was found next? Well, I know I'm going on average 5 meters per second for 0.006 meters. How do you find time? Multiplying them will not gonna quite work. If I do, just looking at the units, if I did meters times meters per second, I get meters squared per second, which definitely is not a time.
Divide the velocity divided by gravity plus time.
The 5 divided by 5? You're talking, what are you, I assume dividing by this? Is that what you said? Dividing, I got 3 different velocities or speeds here.
Would you do 5 divided by 0, 12.006?
The average speed?
All right, so if I've got something going 10 meters per second and then stops in 0.006 meters, so 6 millimeters, something like that. Quick time or large time or small time? Okay, so if I do, what did you say, 5 divided by 0.006? What is that? Oh, okay, big.
So point
That'll,
oh six divided by 5,
yeah, it's gonna be that.
okay.
Because how far you've gone is your average, how fast you're going on average times the amount of time, so basically, average times time. So that's 0.006 is equal to 5 times time. So 0.0012 seconds. So I now know how much time it takes to stop, and I think the last question is, what is the acceleration?
It's gonna be a big number, right?
Pardon?
Is that gonna be a big number?
Yes, it should be a big number. I think I said make down positive,
Yeah, you sit down as positive.
all right? So how do you find acceleration? What is the formula?
Velocity over time.
More specifically, I heard velocity. over
Average
time.
velocity over time.
Change.
No, I'm sorry.
The change in velocity, the change in time.
Yes, change in velocity.
Delta velocity.
Well, the time we just figured out, that's 0.0012 seconds. Change in velocity, that's, what is my change in velocity? So if I heard you correctly, and it's possible I didn't,
5 meters per second.
no, that's not the change.
10
Close,
meters per second.
no, close,
5 meters per second?
no. But someone's got your back. How do you find change?
Initial minus final, or final minus initial.
Final minus initial.
5
0 minus 10.
Oh.
is 10.
So negative 10 over 0.0012, which is something absolutely spectacular.
Would, do you keep it as an accurate?
Excuse me?
Does it stay in
Yeah, because I believe I asked for the vector acceleration and I made it down positive.
Yeah.
So the fact that the acceleration is upwards needs to somehow be indicated. And so you'll end up with something meters per second squared, negative something. 8.8. $8,333 meters per second squared, negative. Is that, okay.
Yeah.
That'll kill you. It's not the fall that kills you, it's the stopping. Typically. I could also see if I were falling out a window, having a heart attack on the way down. Questions on this? Other questions?
I have a question on number 2.
Which one's number 2?
Is the match the quantity for the appropriate, height?
Okay, the scalar vector, neither either?
Yeah,
Okay.
so when we went to talk to Mike, the tutor for jerk, I had it as a vector, but he said that it could be either, but to
For which one?
jerk. But he said to double check with you, cause he thinks it could be either.
I've only seen jerk defined in terms of vector acceleration, so I would say jerk is a vector.
And he said the same thing as acceleration, that it could be probably either.
Yeah, acceleration could be either.
And then for number 3, the object that dropped towards the ground below, you said what is the acceleration due to gravity, but you didn't specify where we were. Were we supposed to assume that we were on Earth? Okay.
If you made that assumption, you got part correct.
Okay.
Bless you. Yes.
I have a question, we have a question 15 with the different velocity, acceleration, velocity, and position.
Right.
And the question is for the accelerations, are we able, I guess, how do you figure it out to use, not identifying the else?
Of whether you're speeding up, slowing down, or neither? You can't. All we could figure out from an acceleration time graph without more information is change in velocity. But we have no idea if that's speeding up or slowing down without knowing the velocity, so
So I just wait and use those.
probably not.
Okay.
Yeah, not everyone's gonna be used.
Okay.
Other questions? Were you just seeing if anyone else had a question, or you're done?
I always have questions,
Okay.
but. I feel really about it.
All right.
Can you go over, I'm so sorry, can you go over question 9, the definitions?
What was
For
9?
each circumstance, below describe a situation in which it can happen or any if it's not possible, and explain why.
Okay.
So I think I got A right. But I was having trouble with C, D, and E.
All right, I don't remember which C, D, and E are.
C's displacement is constant and the acceleration is constant but not zero.
All right.
They're both not zero.
First off, and this shows up in that linear motion lab too. What does constant displacement mean?
It's constantly moving. It's constantly moving
How?
because the displacement is direction and.
What is displacement?
I thought displacement is where you're at from when you start. from the
Okay.
starting point.
So if that's constant,
and
what does that mean?
That's not good. I'm in the opposite direction there. Yeah.
So is that, if it's constant, it's at rest?
Yes,
Not moving.
a constant displacement, same as constant position, you're at rest.
You're at rest. So you can have a constant acceleration.
All right, if you are
Oh,
at
no,
rest,
you can't.
what would the acceleration be?
Zero,
Yeah,
which is, that can be constant.
it is a constant,
It
it's
is.
just not non-zero.
Oh, but it says not
Oh,
zero. So
yeah.
it's, okay.
Because I think you said non-zero.
It did say non
Yeah,
zero.
it is, it's a constant zero acceleration.
Okay.
Yeah, there are a number of people who go with constant displacement means you're moving the same amount in the same direction for a particular time period, but we're not talking in a time period. Constant displacement by itself, it's, you are in the same position relative to your starting point. That is not changing, so therefore you are not moving.
Alright, and then,
And we are not considering spinning in place, as some students want to do.
and then D is, acceleration is not constant, not zero. And then acceleration is constant.
All right, so after the word acceleration, I should have A with a vector symbol or A without a vector symbol.
You have A with a vector symbol and it's not constant, comma, acceleration, A with no symbol is constant.
All right. So what's characteristic of a vector?
Direction,
Direction,
And,
speed,
magnitude,
yeah,
what,
magnitude.
magnitude.
so we have some size, some direction in order for it to be a vector. So if I had any vector, and it doesn't have to be one we've studied, I have some vector, we're using X, let's try something I'm not using for anything else. I have some vector Q. It has some magnitude, and the magnitude of Q is gonna be Q. The direction is gonna be some angle. And what I'm saying is it possible for this not to be constant, but this to be constant? Well, that has two parts to it. If part of it's constant, what does that say about the second part?
It has to be.
No.
No, it doesn't.
If this is not constant, I know at least one of these is changing. So in terms of velocity, velocity is a speed in some direction.
Yeah,
All I know, if my velocity is constant, that means they're both constant. If my velocity isn't constant, that means either my speed is changing or my direction is changing. Or both. So that one, I think you have a non-constant acceleration vector, but a constant acceleration scalar. Or is it the other way around?
Yeah, right.
No, yeah, right.
That's right, okay.
and then, E is displacement is constant, not zero, and velocity is not constant.
Say it one more time.
Displacement is constant, not zero,
Okay,
and velocity is not constant.
all right. So if your displacement is constant
It's still.
and not zero,
There, that's what it is.
yes, that, I mean, ultimately, that's it. What does the non-zero constant displacement mean?
Not zero. Constant displacement.
So constant, first off, constant displacement, we talked about earlier, but was said again. Constant displacement means correct. And not zero means,
It has moved, but it's not currently moving.
yeah, you're no longer at the starting point. Most of you go wherever you're going after this. At some point, you're gonna be sleeping. At that point, you're not moving. The fact that you moved throughout the rest of the day is irrelevant. The fact that at that moment, your displacement is zero. Sorry, your displacement, potentially it's not zero, and constant. Probably not the best example.
Well, you wake up in bed and you fall asleep on the couch that night.
There we go. Better. Other questions or follow-up questions? All right. Is there any more questions? Let's talk about Newton's third law. We've already done Newton's third law before, just did not express it as Newton's third law. Most of you know it in what I consider the cringe-worthy version.